And so as I mentioned several times before in the prior videos, there are hyperparameters for machine learning algorithms that that could potentially impact the accuracy based on their settings. So there's a need to have methods in place to try to optimize those settings to get the best models that we can get given the data and predictor variables that we have. So in this section, we're going to look at some of the common methods that are applied to that problem, and then also look at how those are applied in caret specifically. Okay, so depending on your algorithm, there'll be a different number of sample or hyperparameters that will need to be tuned or determined. So for example, with k-nearest neighbor, we're generally just looking at the number of neighbors. I guess you could also look at the measure of distance. Neural networks notoriously have a lot of parameters that need to be set. As you can see here, again, we're really not talking about neural networks much in this course. Decision trees, you have your pruning parameter, like the CP parameter and R part. Boosted decision trees, such as add a boost, you have to provide the number of trees. Random forest has the number of variables to select at each node and also the number of trees. Support vector machines with a polynomial kernel needs a polynomial order and then a cost parameter. Support vector machines with a radial basis needs gamma and a cost or slack parameter. So again, there's a need to figure out how to optimize these things. Here's an example of a study that looked at this issue in a remote sensing context. So this is for support vector machines specifically. And here we're trying to determine the impact or assess or map or whatever the impact of the order of the polynomial for the polynomial function versus the gamma parameter for the cost function. I think that's what they're optimizing here. Yeah. Is that what they're optimizing? Oh, yes, yes. So they're optimizing on gamma. You see that there. Okay, so as you can see here, it does seem like there is a pattern. So we're seeing generally increasing performance with higher polynomial order, most of these cases. And then maybe not as much of a pattern here for gamma, but maybe a bit of a pattern. What I've generally found is whether or not you need to optimize tends to be case specific. So you can't really know for sure. So that means to make sure you obtain the best model, you generally should go through an optimization process. Okay, so we're going to look at some of the methods used to try to determine the best or optimal settings. So method one is holdout. So you basically take your data and you split it into training and testing data. So there are separate splits that don't overlap. You create a model on the training sample, and then you test the model performance as you change the different hyperparameters on the test data. Because again, you're trying to look for a model that generalizes well, so you don't want to assess it on the test data. So the parameters that provide the best prediction on the test data then would be considered the optimal parameters. So in many ways, this is probably the best way to do it, but the issue is you're having to throw out samples that you could have used in training because you're holding them to assess the model. And when having more training data tends to improve the model, and we don't always have a ton of training data points, this is generally not a method that we can use because of those limitations. So there are other methods. Okay, another option is leave one out cross-validation. So this is how it works. So the model is trained on all of the samples but one. So you hold out one validation sample. Then you predict to that held out sample. Then you run that k times, where k is equal to the number of samples. So basically you do this a number of times that's equal to the number of samples you have, such that every sample is held out in one of the models. And then you compute an average over that, and then the one that provides the best parameters based on that average is considered best. I tend to not use this method. I think it's not the best given some of the other options, but it is sometimes used. I've seen it used specifically in the context of like k-nearest neighbor, for example. K-fold cross-validation is what I commonly use the most, and here's how it works. So the data are randomly split into k-folds or subsets, for example 10 in the case of like 10-fold cross-validation. So the model is created using k minus 1 folds. So if it was 10-fold, it would be 9 minus, or 10 minus 1, or 9, and is ran k times, so that one fold is left out at each time. So imagine you have 10 pieces, 10 subsets of data that don't overlap. So you're going to run the model 10 times using 9 of them and holding out one of them each time, and that one that's held out will always be different, so that all of the 10 samples are held out in one of the models. And then you'll average those out to assess the performance, and the one that provides the best predictive power averaged across the different folds will be the preferred model. K-fold cross-validation with repeats is basically the same thing, except that instead of just doing this once, we're doing it multiple times. So for example, if we did 10-fold cross-validation with 5 repeats, you would do one set where you have 10 folds that are mutually exclusive. Then once that's through, you would shuffle the data again, create a new set of folds, and redo the process. And you would redo that as many times as you set for the repeat. So again, like if you had 10-fold cross-validation, 5 repeats, you would do it 5 times using 5 different random folds or data partitions. So that just adds a little bit more variability in your folds. So hopefully that'll allow you to, to get measurements that are more accurate because it's seeing more variability in the data. That's the idea. Okay, bootstrapping sounds a lot like k-fold cross-validation, but the key thing here is that the folds are not, or the data partitions are not the same each time you validate the model. So the data are split into a training and a test set. Again, 2/3 and 1/3 are common. This is repeated multiple times using different random training test splits. So again, with k-fold, you've got separate sets of data, and you're not reshuffling them. With bootstrap sampling, you are reshuffling them each time. And again, you're just going to use the one that provides the best prediction on the prediction of the withheld data from the bootstraps. So you can think about this again as random sampling with replacement. It's the same thing we talked about with random forest. So k-fold cross-validation, the folds are consistent. Bootstrapping is random in and out each time, or training and test each time. All right, so a grid search. So we talked about how you can assess it using your available data, but how do you determine what values to actually assess? So with a grid search, you basically specify what values for each of the hyperparameters you want to test, and then it'll go through and test all combinations. So for example, in this made-up space, we have a parameter which has values A, B, C, and D, and we have a second parameter that has values 1, 2, 3, 4, and 5. So the algorithm would have to search through every combination of hyperparameter 1 and hyperparameter 2. So A and 1, A and 2, A and 3, A and 4, A and 5, B and 1, B and 2, B and 3, B and 4, B and 5, so on and so forth. So if you're using k-fold cross-validation, you would have to go through that process for every single combination, and then you would return the one that provided the best performance on the withheld data. So as you can imagine, that can be very memory intensive. So I've ran grid searches that have taken a day before, because you have to look at so many different combinations. So that's actually one of the negative components of machine learning. Creating a single model generally doesn't take too long, unless you're talking about doing like something complex deep learning. But if you need to optimize it, it can take a really long time just to test through all these different parameters and combination of parameters. So imagine if you had 3 hyperparameters and you're trying 100 values of each. So it'd have to do every possible combination of each of those 100 by 100 by 100 values. And it'd have to run that through like a k-fold or a bootstrapping method to assess it. So again, it can be very slow, but it's kind of necessary, because these hyperparameters can impact the performance, so they need to be optimized. Okay, so what method should you use? So here are some things to consider. So the number of training samples available. So the more samples you withhold to either validate or test the model, the less you're going to have to train it. So that's one thing that precludes the use of the holdout method. The algorithm being tuned could have an impact. The number of tuning parameters, that impacts the speed and the size of the grid search. The number of different values you want to try for each tuning parameter, and then again the time and computational requirements to actually do that process. Again, it can be fairly time consuming. Generally, I tend to use either k-fold cross-validation, repeated k-fold cross-validation, or bootstrapping. With k-fold cross-validation, I tend to just set it to 10 unless I don't have a lot of samples, and then I'll use like 5 so that the folds aren't very small. It's good if you can to do some repeats because, again, it's just more variability, so it allows you to actually just assess the data or the optimization in a more robust way. So that's just my 2 cents, but again, it's kind of case specific. Okay, so what is actually optimized? Well, again, that depends on the algorithm. So here are just some examples. So again, for K and N, we need to do K. For decision trees, it's the complexity parameter, the pruning criteria, so like the CP. Boosted decision trees is generally the number of trees or iterations. Random forest has 2 parameters. SVM, you've got gamma, or the polynomial order, the cost parameter. So those are things that you'd have to optimize or should try to optimize, but then the other question is what values do you actually have to try? So here are just some suggestions, and then I just got this from the literature. So 1 to 20 for the number in K and N, 0 to 1 for the complexity parameter, 10 to 1,000 trees for boosting, random forest 10 to 1,000 trees. mtry, there actually is a limited number, so it's basically 1 up to the number of variables that are available. For SVM is particularly hard to optimize because there's effectively just an infinite number of possible combinations. So for the C, I tend to use 10 to the negative second up to 10 to the second, so maybe multiple orders of magnitude. And then if you wanted to be more specific, once you've narrowed it down, you could do it again over a smaller range. And then gamma, -4 or 10 to the negative fourth to 10 to the second, again, you could narrow that down in a second round. Okay, so how do you actually do this in caret? So generally this is done by setting up training controls using the train control function. And here's an example. So I'm creating an object called train control, and then I'm calling the function train control. So I'm saying the method is CV, so that's cross-validation. The number is 10, so I'm doing 10-fold cross-validation. And then this verbose, it is equal to true, means that it's actually going to print results as it goes, so you can see how it progresses. There are different methods available inside of caret and that can be called inside of this function. So bootstrapping is called with boot, k-fold cross-validation is called with CV, repeated k-fold is repeated CV, and leave one out is LOCV. If you're doing k-fold cross-validation, the number will define the number of folds. If you're doing bootstrapping, it'll be the number of iterations, like resampling iterations. For repeats, that's if you're doing with repeats. So if you do repeated k-fold cross-validation, this is the number of repeats. So if we went up here and we change this to repeated CV, we could do numbers equal to 10, and then repeats is equal to 5 to get 10-fold 5 repeat cross-validation. Okay, so once you've actually created that object, you need to actually call it within the training model so that it actually knows how to set up the tuning process. So there's 2 broad ways to define what values you want to set. So you can do tune length. So in this case, you just give it a number, and it'll just pick 10 numbers across a range, in this case, to assess for each thing that it has to optimize. So if you were doing the K and N, it would just do 10 different values for K. So you don't really tell it what values, it just picks a certain number of values to try. Obviously, the larger you make that number, the longer it's going to take, because the more things it's going to have to work through. Here, another option is you can do tune grid. So in this case, you actually give it a grid of values. So here I use this expand.grid argument, and I'm saying for K, test 3, 5, 7, 9, 11, 13, and 15. And then down here inside of the model, instead of calling tune length, I call tune grid, and I call that list of k values to call. If you got more than one tuning parameter, then you can do you can set it up as like k is equal to a set of values and then comma, and then the other parameter is equal to another set of values. And then lastly, there's this tr control argument, and there we're providing the training controls that we specified in the prior slide. So that's how it knows that you want it to do tenfold cross-validation and then print the results in verbose way. Okay, and another complexity of this is what are you actually trying to optimize for? So what you can optimize for depends on what you call in summary function and then also in train control. One option is multi-class summary, and in that case it's going to look at overaccuracy and kappa, and generally the model with the highest kappa is used, but you can specify overall or kappa. For two-class summary, you can do the model with the best sensitivity, specificity, AUC, or AUC from the ROC curve. And there's also other options for continuous variables. Okay, so here's some options again for classification with multi-class. You can optimize for best kappa or best accuracy. For probabilities, ROC. For a random forest, because it has that out-of-bag thing, you can do that out-of-bag. And then for regression, you can optimize an RMSE or R squared. So here's that example here. We're telling it to optimize on kappa specifically. Okay, so one complexity with machine learning is that there's a lot of randomness built into most of these techniques. So if you run the algorithm once, you're not going to get the same example each time. So if you wanted to make your results reproducible so that you could share it with someone or include it in like an appendix for a paper, it would be kind of frustrating because they would run the model and get something different or slightly different. So one way to make your model reproducible so you actually do get the same result each time is to set a random seed. So within R, there's a built-in set.seed function, and if you set that, that will produce the same result each time. So in a simple example, if you had a random number generator like R, using like the R norm function or the sampling function, you could call set.seed before it, and that you would get the same random set each time. So that helps with reproducibility. For machine learning specifically, you can't just call it at the beginning of your code. You'll need to do this before any step that has any random component, so that the randomness is I guess subverted before each step. All right, so in the last video, we're just going to look at a couple specific things related to changing your feature space and doing data pre-processing. But we're nearing the completion of the background material before we move on to actually doing some of this in R.